and welcome to our class on wheel analysis. In today's class, we want to prove the uniqueness of a limit. We want to prove the uniqueness of a limit. That implies that we want to prove that the limit of a sequence is unique. And we want to show that a sequence has just one limit. A sequence can only have just one limit. There are two ways by which we can prove this. We can prove it using the contradiction approach, just as we used in the previous video. We can prove it using the contradiction approach, or we prove it by the direct approach. For today's class, we'll be using contradiction approach. We want to prove by contradiction that the limit of a sequence is unique. That the limit of a sequence is unique. Proving by contradiction. That implies that we want to prove that the limit of a sequence is unique using contradiction approach. Using contradiction approach. But we'll remember that a sequence can only have a limit if and only if the sequence is convergent. Note, a sequence only has a limit if and only if it is convergent. If and only if the sequence is convergent. Therefore, to prove it, let A be that sequence such that it converges to A and B. Such that it converges to A and B. Our sequence AN converges to A, and the same sequence AN converges to B. Since we are proving by contradiction, we want to assume that A is not equal to B. Assume A is not equal to B. And if A is not equal to B, then one is greater than the other. Let B be greater than A. Let B be greater than A. It means that if the sequence AN converges to A, as N gets bigger and bigger, AN gets arbitrarily close to A. Maybe we should just write it down. As N gets bigger and bigger, our sequence AN gets arbitrarily close to A. And if AN converges to B, the same thing happens. As AN, if AN converges to B, if AN converges to B, also as N gets bigger and bigger, the sequence AN gets close to B. The sequence AN gets close to B. But A and B, they are distinct numbers. And if A and B are distinct numbers, it means that our sequence AN is getting arbitrarily close. Gets arbitrarily close to two distinct numbers. Our sequence AN gets arbitrarily close to two distinct numbers. These two distinct numbers will have a distance between them. Let's consider it on the number line. Let's consider it on the number line. It is our number line, and this is our A, and this is our B. And our AN is converging to A. Let's look at a radius epsilon, or an epsilon radius rather, around A. That's an epsilon radius around A, and also an epsilon radius around B. It will be something like that. An epsilon radius around B. What does this tell us? As we can see on the number line, if the sequence an converges to A, then it implies that given any epsilon greater than 0, then the terms of the sequence will eventually get within epsilon of limit A. The terms of the sequence will eventually get within epsilon of limit A. And if an also converges to B, the same thing happens. The same thing happens. Therefore, same thing happens if sequence an converges to B. Therefore, the smaller the epsilon, it implies that the terms of the sequence will belong to two disjoint intervals at once. Belong to two disjoint intervals at once. Now we want a value of epsilon that can force this contradiction. We want a value of epsilon that can force a contradiction. Remember, we have said that our A is not equal to B. I have said that our A is not equal to B. Now, if we assume that epsilon is equal to B minus A, if we assume epsilon to be equal to B minus A, that will not be enough. That will not be small enough to force this contradiction. Remember, I said we want an epsilon that can force the contradiction. Since A is not equal to B, and by assumption, we have assumed that B is greater than A. Therefore, we want to let our epsilon to be B minus A over 2. Let epsilon to be B minus A over 2. Therefore, by definition of convergence, if for any epsilon equals to B minus A over 2, then there exists a K1 belonging to the set of natural numbers such that an minus A will be less than epsilon for all n greater than or equals to K1. And what does that mean? That implies that an minus A will be less than or equal to what's that? Less than what? What's our epsilon? B minus A over 2. The same thing applies when the sequence an converges to B. If an converges to B, then again, as we have there, for any epsilon equals to B minus A over 2, then there exists a K2 belonging to the set of natural numbers such that the absolute value of an minus B will also be less than epsilon for all n greater than or equals to K2. And again, that implies that the absolute value of an minus B is less than B minus A over 2. Let K to get a K that works, we say let K equals the maximum of our K1 and K2 for all n greater than K. It implies that what? Our an minus A is less than or equal to B minus A over 2. Now, we recall our equivalence. We call our equivalence rule that if the absolute value of C is less than or equal to C, then it means that what? Minus C is less than A is less than C. That implies what? Minus B minus A over 2 is less than or equal to an minus a is less than or equal to b minus a over 2. And so this gives us what? A minus b over 2 is less than or equal to an minus a, the sequence an minus a, and that is less than or equal to b minus a over 2. When we add a all through, we have a minus b over 2 plus a, less than or equal to the sequence a minus a plus a, less than or equal to b minus a over 2 plus a. And so by the time we work on this, we have a plus b plus 2a over 2, less than or equal to an, less than or equal to b minus a plus 2a over 2. This gives us what? B plus 3a over 2, less than or equal to the sequence an, less than or equal to b plus a over 2. Also, for all n greater than or equal to k, our an minus b is also less than or equal to b minus a over 2. Again, by rule of equivalence that we have seen there, we have minus b minus a over 2 to be less than or equal to an minus b, less than or equal to b minus a over 2. And that gives us what? A minus b over 2 less than or equal to an minus b, less than or equal to b minus a over 2. By the time we add b all through, just as we added a all through here, we are going to have a plus b over 2 to be less than or equal to an to be less than or equal to 3b minus a over 2. And from there, it shows us that what? Our an is less than, let me use the red marker. Our an is less than a plus b over 2, and still a plus b over 2 is also greater than an. B over 2 is also less than or equal to an, as you can see in the circled portion. And this is not possible. This is not possible. That is a contradiction. Therefore, our an is less than or equal to b plus a over 2. And as you can see again, when it converges to b, that a plus b over 2 is less than or equal to an. Therefore, this is not possible, which implies that this is a contradiction. And so it implies that the limit of a sequence is unique. The limit of a sequence is unique. So we have been able to prove by contradiction that the limit of a sequence is unique. If you have gained anything from today's class, give the video a thumbs up, share with your other colleagues. Thank you. God bless you. I see you in the next video.